Hey guys, it's Miss Manili, and I'm going to give you a tutorial on the next lesson, which is beginning chapter 10 on comparing two populations or groups. So far we've looked at inference for just a single sample from a single population, and we've been analyzing either the sample proportion or the sample mean, either to estimate the parameter or to test a claim on the parameter. So in the next couple of lessons, we're going to be looking at comparing two groups. So for example, if I were doing an experiment and I wanted to see if there was a significant difference between the reaction to a treatment versus a placebo, I would need to do a hypothesis test comparing the two groups. So today's lesson is going to be looking at comparing two proportions. So the outcomes for today's lesson are basically to understand the sampling distributions for the difference between two proportions, and look at conditions for inference, and then also to perform a significance test comparing two proportions. And you're going to see that all the processes that we go through are just very similar to the ones that we've already done with single samples. The formulas are a little bit more complicated, but we'll get into them later. So I don't know if this is in the notes or not, but suppose we want to compare the proportions of individuals with a certain characteristic in population 1 and population 2. So if we call those parameters p sub 1 and p sub 2, then we've identified the parameter for each population. The ideal strategy is to take a separate random sample from each population and then to compare the sample proportions with that characteristic. Well, what about if we want to compare the effectiveness of treatment 1 versus treatment 2 in a completely randomized experiment? Well, this time P1 and P2 represent the true proportion of successes or outcomes for each of the treatments. And so again, we can use the proportions of successes in the two treatment groups to make comparisons. And so sometimes it's going to help with these problems because you're going to be given a ton of information to actually create a little table where you outline, where you identify like what you're calling population 1 and what you're calling population 2. You don't have to call them 1 and 2. You can label them with subscripts like T for treatment and C for control if you'd rather do it that way. But you do want to have some way of identifying the two different populations. The parameters obviously are going to be just our single P with the appropriate subscript, and then our sample statistic is going to be P hat. And then we have our sample sizes. So we're going to be drawing two different samples from the populations. The sample sizes do not have to be the same size. So if we want to look at significance tests for the difference in two proportions, an observed difference between two sample proportions can reflect a difference in the populations, or it simply could be due to chance variation in random sampling. So significance tests help us decide if the effect that we see, if that difference is due to chance or if it's really due to a difference in the two groups. I'm going to start off with this example, and then I'm going to jump to another one in just a second that's not part of your notes, but I think it'll help illustrate the sampling distributions for you. So in this particular example, we're looking at the National Sleep Foundation asked a random sample of U.S. adults question about their sleep habits. One of the questions asked about snoring. Of the 995 respondents, 37% of adults reported that they snored at least a few nights a week during the past year. Would you expect the percentage to be the same for all age groups? So if we take that sample and split it up into two different categories and two age groups, we can see that 26% of the 184 people that were under 30 snored, compared with 39% of the 811 in the older group. So what we want to know is this difference of 13%, is it a true difference between the two groups, or is it something that could have just happened by natural variation? And so to answer this question, we need to do a hypothesis test. And the parameter of interest now isn't just a single population proportion, it's going to actually be the difference between the two proportions. So if I were stating the null hypothesis, if I wanted to call, let me see if I can get, whoops, it disappeared on me. Okay, so if I wanted to state my hypotheses, I'm going to need to first of all identify which group is which. So if I call, like, if I just, label P, I'm going to have 30 minus as one of them, and then I'll have my P, and I'll have my over 30 group here. So those could be the two parameters I use, or if I want to label my under 30 group as population 1 and my over 30 group, that actually might be a little bit easier. I have the older group, and I call that population 2. My null hypothesis now, and you can write it a couple different ways. We can either say that the null hypothesis, which would tell us basically that there's no difference between the two groups. I can write it two ways. I can either say that P sub 1 is equal to P sub 2, and we're just looking for a difference. So my alternative would be then that P1 is not equal to P2, and that would be the proportion of people who snore in each of the groups. And I apologize for my handwriting. It's really hard for me to write on my slate at home. Another way, though, and this is the way that I would recommend stating your hypotheses, is to look at it actually as a difference. So if I were to subtract P2 from each side, my null hypothesis then, to show that there would be no difference, would be to say that P1 minus P2 is equal to 0. And if I think there is a difference, then I'd say P1 minus P2 is not equal to 0. And so, excuse me, when you're dealing with a difference in proportions, you can express your null and alternative hypotheses either way. I do think it's a little bit easier with the rest of the notation that we're going to be using to be consistent. I do think it's easier to actually describe your hypotheses as a difference between the two proportions. However, you do, in your definition, remember how we always have to define our parameters? You're going to want to make sure that you define, so it's going to be the difference in proportions of, sorry, this is terrible, in proportion of people who smoke, or people who snore, but you're going to also want to indicate that you're doing the under 30 group minus the over 30. So you want to make sure that you're defining how you're doing the subtraction so that it's very clear to anyone else who's reading your results. Now I'm going to totally switch gears, because in order to conduct a hypothesis test, you really do need to understand the sampling distribution, because that's how you're going to find the probability of seeing the result that you saw. So we have to understand the sampling distribution for the difference in two proportions, and so I'm actually shifting gears and I'm going to be looking at a different example. And I don't think this was in your notes. So if we wanted to explore the sampling distributions between the difference between two proportions, let's start with two populations that we already know about. So suppose we have a school where 70% of the students did their homework last night, and then we have another school, we'll call it school 2, where only 50% of the students did their homework last night. Since we're dealing with a P, a sample proportion, all we really need to know is the size of the sample, and then we can determine the sampling distribution. Because remember, the mean of the sampling distribution is just going to be the proportion, and then the standard deviation is going to be P times 1 minus P over N, take the square root of that. So school 1 was just a simple random sample of 100 students, and at school 2 we had a simple random sample of 200 students. So what we want to know is the sampling distribution of the difference in two proportions. So if I were to actually subtract, you take two samples, subtract the proportions, and then take another two samples, subtract the proportions, and then track all of those values, I'd have a sampling distribution for the difference. So this next slide kind of shows you each case. So this first graph would be population 1. So this is the sampling distribution at that school. If you remember, we had 70% of the student body did their homework. We had a simple random sample of 100 students. And so our sample varies from, it looks like about 56% to about 84%. Now, in the other school, we had only about half the kids did their homework, but we had a bigger sample. So we should expect that the spread is going to be a little bit less than in population 1. So this is population 2. And so notice that the distribution is normal. It's centered around 50. The other one was centered around 70. And the spread now only goes from 40 to 60. So it's a little bit smaller. It's about 20 here. And the first one was almost 30%. So now if I subtract them, I would expect that if I subtract, the difference in the means should be 20%. And so that is where the new distribution is centered. What might surprise you, though, is that the spread actually increases. So now my spread is going from, looks like about 2.5% to about, I don't know, almost 38%. So we've got a really big spread here, bigger than the other two. And that's essentially because when I'm adding random variables together, I ultimately have to add their variances. I'm sorry, when I'm subtracting random variables, I still have to add their variances. And so when we're talking about the shape, center, and spread, this is the sampling distribution now of the difference in proportions. So I have to understand a formula for coming up with a mean and coming up with a standard deviation. I can see that the distribution is approximately normal, so we also have to talk about the conditions that lead to that, just like we've done with means and proportions for a single sample. Okay, so this is what you're going to want to jot down on your paper. So if we're dealing with a sampling distribution for the difference between two sample proportions, we got to remember that p hat sub 1 and p hat sub 2 are both random variables. And so if I'm dealing with this statistic where I'm just subtracting the two, then I'm looking at the difference between two random variables. And a couple chapters ago, we learned how to find the mean and the standard deviation when we add random variables or multiply by a constant or subtract them. And remember, the rule for means follows whatever we're doing with the random variables. So if I'm subtracting P1 minus P2, then I'm also going to do the same thing with the means. However, remember, we don't have any rules for standard deviation, so we have to work with variance. And the rule for variance says that even if I'm subtracting the two random variables, I'm still going to add the variances. And so ultimately, if I want the standard deviation, remember the standard deviation is just the square root of your variance. And so I can put all this stuff together with what I know about sampling distributions and proportions, and I get all of my formulas. So if we're choosing a simple random sample of size, we're going to call it n sub 1 from population 1, with a proportion of successes P1, and independently choose another simple random sample from another population, we'll use the subscripts 2 here, then the proportion of success would be P sub 2. So the center of this distribution, of the distribution of the differences, the mean, as you can expect, I'm just going to subtract the two proportions, and this is going to be the parameters. I'm subtracting the parameters. And if we're dealing with a significance test, then I'm assuming things are true. The standard deviation, remember, is going to be the square root of the variance. In this case, I'm adding the two variances together. And so this would be your formula. It's very complicated. You don't actually need to know this. You're not going to be asked to find the standard deviation, but it's just good to kind of pull everything together, I think. This is your standard deviation of your first population. This would be the standard deviation of your second population. If I square them and add them together and take the square root, that's how I get this formula. Now notice again, for the standard deviation formula, I still have to make sure that each population is greater than 10n, and this distribution is going to be normal, and notice that now I've got 4 different conditions. They're the same conditions that we've been dealing with. I just need to make sure that all my successes and all my failures are greater than 10. But this time I've got 2 different populations, so I have to double check that the number of failures in my first population and my number of failures in that population are all greater than 10. All right, so this is just an example. Obviously, our distribution is going to be normal. The center of that distribution is just going to be the mean, P1 minus P2. We've got our standard deviation, and then this is the sampling distribution. Okay, well, a lot of times we don't have a population parameter. So, for example, if I were doing confidence intervals, so this is actually more for confidence intervals than it is for hypothesis tests. But if I were doing a confidence interval, I wouldn't have a parameter to start with, so I'd have to rely on my sample statistic to calculate the standard deviation. And when I do that, it becomes a standard error. And so it's essentially the same exact formula, except instead of using the claim, I'm using my sample proportion in the formula. Now, if we're doing a test, we're usually assuming the null hypothesis is true. And if the null hypothesis is true, then we're basically saying that there's no difference between the two proportions. So if there's no difference between the two proportions, it's the same as saying that they came from one population. So we do this thing called pooling. And I know this seems kind of confusing, but it really isn't. You'll see. When we pool, instead of looking at samples coming from two populations, what I do is I just take all of the successes in both samples and then I total the samples together. So for example, if I'm looking at boys and girls, and let's say I had 3 girls out of 10 and 5 boys out of 15, well, I know my p hat for girls is going to be 3/10. My p hat for boys is sorry, my handwriting is terrible on this thing, is going to be 5 out of 15. But if I wanted to do the pooled p-hat, and I basically just do p-hat and I write the word pool here, I'm basically going to take all of my successes, and in this case they were 3 successes in the girl group, 5 successes in the boy group, and that's going to be 8 successes out of the total in my 2 samples, which would combine to give me 25. So that's how we find a pooled p-hat. Your calculator does all of this work for you, but just in case you're ever asked like a multiple choice question about pooling, that's all it is, where you're just totaling your successes and dividing by the total in your samples. The standard error formula then becomes a little bit easier because you're just going to use your pooled proportion and then multiply it times 1 over n sub 1 plus 1 over n sub 2. And again, your calculator does this all for you, so it's not as complicated as it looks. So when we're looking at a test for the difference in 2 proportions, remember when we're dealing with proportions, we're dealing with a normal distribution, and so we're going to be ultimately using the standard normal curve, and we're going to be calculating a z-test statistic, just like we did for a single population proportion. And so our hypotheses, like I showed you in the other example, can be written one of 2 ways. I would recommend writing them this way as an actual difference, and your null hypothesis then will pretty much always be that P1 minus P2 is equal to 0, because we're assuming that there's no difference. Now, if you're dealing with a specific situation where you expect the difference to be 5, then you might say P1 minus P2 is equal to 5, but for this course, we really are just looking at either there is a difference or there's not, and so usually we're just setting this equal to 0. Okay, for the alternative then, and notice there's 2 ways you can write the alternative. We can either think that the proportion in the first population is greater than the second or less than, or just simply not equal to. But again, I think it's a little bit more helpful to write it using a difference in proportions. And basically what we're going to do is we're going to calculate the difference in the samples, standardize it using the mean and standard deviation from the sampling distribution, just like we've done all along, and then we have an upper, lower, or 2-tailed test, just like we've always had. The z-test statistic, this looks like a really complicated formula, but it's really the same thing that we've been doing all along. It's just combining all the formulas together so they look really ugly. But let's actually just go ahead and do this. I'm going to actually skip this sleep foundation problem because it's a lot more challenging because of the way it's presented. It's also a 2-tailed test. And I'm going to jump right into the first practice problem. And so it says, high levels of cholesterol in the blood are associated with higher risk of heart attacks. Will using a drug to lower blood cholesterol reduce heart attacks? Well, the Helsinki Heart Study looked at this question. Middle-aged men were assigned at random to one of 2 treatments. 2,051 men took the drug gemfibrozil to reduce their cholesterol levels, and a control group of 2,030 men took a placebo. During the next 5 years, 56 men in the gemfibrozil group and 84 men in the placebo group had heart attacks. It says to calculate the sample proportions for each group. So what I would recommend doing at this point is sort of just outlining the information that you have. And so I would actually create a little table for yourself where you're identifying the populations and what you're going to call population 1 and population 2, or in this case, I might actually just use a T and a C to represent the treatment and the control group. So if I call, like, if I say, for example, if I say population 1, is my treatment group, and population 2 is my control. This is what I would recommend, just to kind of, sorry, my handwriting is so terrible, just to sort of lay everything out. I'm going to go ahead and first write my my sample sizes, just so I can keep all my information organized. So 2,051 took gemfibrozil, and 2,030 took the placebo. And then I know that 56 men in the gemfibrozil group. So I'm going to actually call this X. X represents the number of successes. Well, in this case, make sure that looks more like a 0. So 56 men had a heart attack in the treatment group, and 84 men had a heart attack in the control group. And you can label them differently. Like if you want to put the control group as population 1 and the treatment group as population 2, you certainly can do that. So the p hat for my treatment group is just going to be 56 out of, that was 2051. Okay, and so what I'm going to do on my calculator is I'm going to store that in a variable since it's not an exact number. I'm going to store that in alpha A. Okay, and so my p hat for my treatment group, I'm going to keep this up here. Was 0.027. And in parentheses, I'm just going to, so I remind myself that I stored it in letter A. And then the p hat for my control group is going to be 84 divided by 2030. And again, I'm going to want to store that. This time I'm going to store that in alpha B. All right, so my control group, 0.041, and I stored that in B. Okay, so that answers question A, calculate the sample proportions. And so in part B it says, we hope to show that gemfibrozil reduces heart attacks, state the hypotheses, and then verify the conditions for inference. Okay, so my null hypothesis is going to be that there's no difference between the two proportions. And so, like I said, you can either say that your proportion for your treatment is equal to the proportion of the control, or you can say that P sub T, your proportion for the treatment, minus the proportion for the control is equal to 0. You can do it either way. This is the way I recommend, though. Your alternative, then, is to say that your treatment group would have had less heart attacks than your control group. So we would say P sub T is less than the proportion in our control group. If I wanted to write it as a difference, then I would expect the difference to be negative. So if I wanted to write it as a difference, I would say P sub T minus my control is going to be less than 0. And so you can write it either way. It really doesn't matter, but ultimately when we start writing down the probabilities, this method, writing it as a difference, is going to be a little bit better. So the next thing we want to do is test all of our conditions. And so if I look back at the problem, I can see that there was random assignment to each of the treatments. So instead of saying it's a simple random sample, I can say random assignment. And when we're dealing with an experiment, that covers your randomness. So random assignment into the two groups maintains that simple random sample. The next thing, because I'm dealing with proportions, is I would want to check all my n times p, n times 1 minus p. I'd want to make sure all of those things are greater than 10. But I'm dealing with two groups. Now in this case, because I don't know what the parameter is for the population, I really do need to use my p hat, or I can simply look at the number of successes in each of the treatment groups, because I don't have a parameter for the treatment group or a parameter to test for the control group, because I'm only looking to see if there's a difference between the two. So in this case, it's okay to use your p hat value in your test, in testing those conditions, n times p and n times 1 minus p. And since you've got 4 different groups, basically what you can say is the number, and just write it out, the number of successes and failures for each group are greater than 10. Because I can see, if I had 56 men out of 2,051, I know that almost 2,000 of the men didn't have a heart attack. And over 1,000 of the men in the placebo group didn't have a heart attack. So you can just write it out in this case. The number of successes and failures for each group is greater than 10. We have the random assignment, and then again we want to assume that each population is greater. So we'd say that population 1 is greater, or population, I guess I should call that a T to correspond with the rest of my subscripts. So population of the treatment group is going to be greater than 20,510 men, and then the population for the control group we'd assume would be greater than 20,300, and that's fine. There's more than enough men to meet that condition. Okay. So now we want to talk about the pooled sample proportion. Remember, the pooled sample proportion is basically when we add up all of the men that had heart attacks. So there were 56 plus 84 had heart attacks, so there were 140. So p hat is equal to 140 out of the total men in the study. So if I go back, I know that there were 2,051 plus 2,030. So there were over 4,000 men that participated in this study. And so if I divide 140 divided by 4081, I'm going to also store that. I'm going to store this in letter C. Okay. Now it asks to calculate the z-statistic and p-value for the test. This is where I'm going to first do it by hand and show you how you would do it by hand, finding the sampling distribution, and then I'm going to show you how to do it on the calculator, which I know is how you're probably always going to do it. But in order to find the z-test statistic, first we have to find the mean. And we know the mean is simply going to be of p hat minus p, the mean of my distribution is just going to be whatever p1 minus p2 is, which we, remember, in our null hypothesis, we said that it's going to be 0. So the mean of my distribution is going to be 0. The difference should be centered around 0. I don't expect there to be a difference. The standard deviation, then, of the difference in the two proportions, this is where I'm now going to use my pooled p-value. And so this formula is basically, let's go back, whoops, is this formula right here. And so if I do it by hand, it's going to be 0.034 times the complement, 1 minus 0.034. It's going to be huge. Times, I'm going to have 1 over the first population, or the first group, which was 2,051, plus the second, which is 1 over 2,030. And that's how I would calculate the standard deviation. Okay, so on my calculator, we're going to have 0.034 times 1 minus, and actually, let me go back. I saved that letter C, so let's make this more exact. I'm going to have alpha C times 1 minus alpha C. And then I'm going to have 1 over 2051 plus 1 over 2030. All right. So my standard deviation is about 0.0056 or 0.006, and I'm going to store that in letter D. There we go. All right, now the z-test statistic. Remember, I'm going to take my true difference, whatever my observed difference is, and so what I'm going to need to do is I'm actually going to have to subtract the my p hat from my treatment group minus my p hat from my control group, and so that's just alpha A minus alpha B. Okay, and notice that it's a negative difference. I would have expected it to be. And then I'm going to subtract my mean. Well, remember, my mean, I'm assuming there is no difference, so I'm just subtracting 0, so I'm actually not going to really need to do anything there. And then I'm going to need to divide by my standard deviation, 0.006, which I saved in letter D. So I'm just going to basically divide that number by alpha D. And that gives me my z-test statistic. Crying in the background is my dog. It's a beautiful day, and she really wants to be outside instead of listening to me make videos for my math class. But she'll be fine. Okay, so there is my z-test statistic, and if I want to find the p-value, then I'm just going back to using a normal distribution. I know the distribution is normal because we tested all those conditions down here. Okay, so if I want to use proper notation to like show my calculations, what I would say is the probability of p hat, this is my treatment, minus p hat of my control. I know it's a less than, if you go back, we said it was going to be a less than test or a lower tail test. I found the difference between my two sample proportions to be negative 0.014. I calculated the or the z-test statistic, and this is why I recommend doing it as a difference. It's easier to write in the probability statement. So I'm looking at the probability that z is less than 2.47, and now the last thing I need to do is just calculate the probability. So I'm going to go into my distribution menu. I'm going to do my normal CDF. It's a lower tail test, so my lower bound is going to be negative infinity. My upper bound, I'm just going to hit second answer. And since I'm dealing with a z-test statistic, I don't have to worry about putting in my mean and standard deviation. I can see that the p-value is 0.007, and that is significant. So before we talk about what that significance means, let me show you how you can do this on the calculator. It really is very simple on the calculator. If you go to Stat, over to Tests, since we're dealing with a proportion, you want to make sure you're choosing a test that has the word proportion in it. And notice in option number 6, we're dealing with two proportion z-test. So since we're dealing with two populations, that's the option you want to choose. Now, when you're entering in your data, notice that it's asking for x1 and n1, not p-hat. So you want to make sure that you're always entering in the number of successes, and it has to be a whole number. So for example, if I just said that like 2% of my first group and 3% of my second group, if I actually try to do 2% and it's not a whole number, you'll have to round. So in this case, again, I'm going to try to be consistent. My treatment is my first population, and so I'm going to keep that there. So I have 56 men in that group, and then my N would be the total of that sample, which is 2,051. And then in my second group, I had 84 who had a heart attack out of 2,030. And then I just have to select my alternative hypothesis, and in this case, P1 is not equal to P2, and then jump to calculate. And it really does give you everything you need. So notice it tells you p-hat sub 1 and p-hat sub 2. The p-hat that you see below that, that is your pooled p-hat. So if we go, oh, I didn't mean to do that. So if we look at my pooled p-hat, you can see that we get the same value, 0.034, 0.034. The p-value that you see there, though, is my probability. And you'll notice that it's a little tiny bit different. I'm wondering if I did something wrong, because we got the same z-value. Did I enter that wrong? Because they should be the same number. Let me double check. So if I hit second distribution, do normal CDF, and I go from negative 99999 to negative 2.47, yeah, I get the same thing. So I'm not sure why there's a difference there, but... Oh, I know what I did wrong. No, I didn't do wrong. Nope. I'm not sure. Oh, it's not a two-tail test. There we go. Sorry. It's a lower tail test. So I think P1 is less than. There we go. Sorry, that's embarrassing. All right. Now it should work. There we go. All right. So obviously you can see it's a lot faster to do this using the calculator. But I did want to kind of take you through the steps because it's quite possible that you'll have a problem on the AP exam that asks you to find the pooled p-hat or references the standard error. You don't have to remember this formula. I don't even know if it's on the test because it's not something that they assess directly. But you do have to obviously understand how to set up and express your probability statement. Now, let's talk about the significance of this value. Obviously, this 0.007, not only is it significant at the 5% level, it's also significant at the 1% level. And one of the reasons for the significance is because both groups are so huge. Remember, if our sample size is really big, our results are going to be more significant. Even small differences are going to be significant. But in any case, because our results are significant, we can reject the null hypothesis. And remember, the null hypothesis said there was no difference between the two groups. So we can reject the null hypothesis and conclude that the gemfibrozil group, the treatment group, actually had less heart attacks than the control group. So there does seem to be some evidence that gemfibrozil does lower the rate of heart attack. Okay, and obviously you'd want to write that down in the words. The other problem that I wanted to kind of go back and show you was this National Sleep Foundation problem. It's a little bit more complicated. Hang on one second, let me deal with my dog. Sorry. Okay, so when it comes to this problem, I'm not going to go through the whole sampling distribution or anything. I'm going to show you how to do it on the calculator because honestly, that's really how you're going to be solving and doing these tests. So if we go back to this example on the National Sleep Foundation, we know altogether that 37% of adults that were surveyed, of the 995, that 37% said that they snored. When we broke the 995 into two groups, though, we had the under 30 and the over 30. So here's my under 30 group, and I'm going to, in red, highlight my over 30 group. Okay, and so we want to know, there's a difference of 13%. We want to know, is that difference caused by chance, or is it really is there really a difference between the two groups? So we want to perform a significance test. Well, I'm going to call my under 30 group 1 and my over 30 group 2. So when I'm stating my hypotheses, I would say that P1 minus P2 is equal to 0. Remember, we don't expect there to be a difference. That's what we're assuming. The alternative, in this case, it doesn't say anything about one group being more likely to snore than the other. So this is going to be a two-tailed test where I'm just looking at the difference is not 0. And again, you want to make sure that you define your parameters and describe the way you're subtracting. So we can say that P1 minus P2 is the difference in proportion of people who snore and we'd have the under 30 minus the over 30. Now you could also do it the other way around and you're still going to get the same p-value. Your difference is going to be the opposite sign and your z-test statistic will be the opposite sign, but ultimately your test, the significance won't change. The p-value will ultimately be the same. The other thing we want to do is make sure that we have tested all of our conditions. So we know that it was a random sample, so obviously both groups were random. The other thing I want to look at is my number, or my successes and failures. And in this time, because I actually know that 37% of the whole group snores, I can use that as the p-value that I use. And I'm not going to go through all of it because I know you're done watching this and we're almost at 40 minutes. But if I were to take 37% of 184 and 37% of 811, I know that I have at least 10 successes and failures in both groups. So if I want to perform the significance test, let's just jump to it. So let's state the type of test we're using. This is a two-proportion z-test. I already know that the difference in the proportions is 13, so I can start off by saying that p hat 1 minus p hat 2. And when I subtract, the way that I'm subtracting, because I'm looking at the younger group minus the older group, that 13% is actually going to end up being negative because 26 minus 39 is going to be a negative 0.13. Make sure you write it as a decimal as well. Because we're doing a two-tailed test, I also have to remember to put that 2 out in front. So the calculator is going to do the rest of the work for me. So I'm going to go over to stat tests. I'm going to choose my two-proportion z-test. But this is now where you have to be careful, because when you enter in that x of 1, it's asking for the number of successes. And I don't know the number of successes. I know that it was 26% of 184. So we can actually do the calculation right here. 0.26 times 184. And what you're going to see is you're going to get a decimal there. So just round it. So 47.84, I'm just going to round that to 48. And know that when you round, some of your values are going to be a little bit off. Like if I were to do this by hand, my numbers, like my z-test statistic, is going to be a little bit different, but it shouldn't make that big of a difference in terms of your significance level. So in my first population, or my first group I had, or my first sample I should say, 184, and then in the second one I want to take 39% of 811. And so again, I'm going to round that. I'll round that down to 316. And then my second group had 811 in it. And this time we're doing a two-tailed test. And so I'm going to go ahead and calculate. And so all I really need to do is 2 times the probability of my z-test statistic. And again, I'm going to use a less than, and notice that it is less, negative 3.27. And the p-value, you do want to make sure that you're choosing the proper p-value. My p-value is the p that doesn't have a hat on it. That's my p-value, 0.001. Okay. And so now we can state our conclusions. Obviously, 0.001 is significant. We can reject the null hypothesis, and we can conclude that there is a difference in the proportion of people who snore in the different age groups. Now, what we can't conclude is that, younger people are more apt to snore than older people. All we can conclude at this point is that there's a difference. If I wanted to know a little bit more about the difference, though, then what I can do is a confidence interval. Now, this is not in your notes, but I'm going to go through it anyway because you can watch, and it's real simple. So if I go to tests, I'm going to scroll down, and I'm going to scroll down to my interval menu, and I'm going to look for the option that asks for 2 proportion z interval. And so again, I think these are the same numbers. I think it carries them through for you, so you don't have to retype it. If I want to do a 95% confidence interval of the difference, now I can see that the confidence interval, so a 95% confidence interval of the difference, goes from negative 0.2006 to negative 0.057. So basically, I'm looking at a difference of between 5.7% and 20% of the difference. And so since this number is negative, and remember I was subtracting the younger group minus the older group, that gives me evidence to conclude then that the older group is more apt to snore than the younger group, since this value is negative. In fact, the older group, the proportion of snorers in the older group is between 5.7 and 20% larger than the control group or the younger group. And let me actually put that down. So we have evidence to conclude that the proportion of people, my handwriting's, you know what, let me just type this. That'll be easier. We have evidence that the proportion of people over 30 who snore is between, what did I say, 5.7% and 20% more than the proportion of those under 30 who snore. And that's using the confidence interval. So you can see that the confidence interval actually gives us a little bit more information than the hypothesis test. The hypothesis test basically just says, let's see, the result is significant. So we can reject the null hypothesis. We have convincing evidence that there is a difference in the proportion of people who snore in different age groups. And you could probably make that a little bit more specific. Let me actually just move this down here so you can actually read it. Okay. And so that's how you would state your conclusions. If there's not a difference, or if the value wasn't significant, then you would just say, the value isn't significant. All right, so you do have a couple more tests to do on your paper for homework. I will just go ahead and tell you to look carefully at number 2, because this is actually a 1 sample situation. So you do get a little bit of practice doing a 1 sample. Problems 3 and, is that the only one?
Problem number 3 then, no, there's a fourth one too. So problems 3 and 4 are 2 sample. And again, you can use your calculator. Just make sure that you're writing down everything that you're supposed to write down. You don't have to talk about the sampling distribution as long as you say that it's a 2 proportion Z test, and that covers that for you. So good luck. We'll go over any questions you have next class.